In this video, I'm going to work through a rabbits versus sheep problem from Strogatz. This is problem 6.4.1. This is on page 184. I'm not going to go through the setup of this problem, but I am going to go through the phase plane analysis and show you how all of these things work. So first of all, here is the system of two differential equations. X dot equals x times 3 minus x minus y, and y dot equals y times 2 minus x minus y. This is what I'd been calling little f of x and y, and this is little g of x and y. So first I'm going to look at the nullclines. So number one, I'm going to set x times 3 minus x minus y equal to 0 and see what kinds of points satisfy just this one equation. Well, since x is a factor, all points where x equals 0 are on the nullcline. And also, all points where y equals 3 minus x. Okay, so let's sketch those and see what happens. Let me see here, where can I put this? Yeah, actually, let me draw the axes in gray. Draw the axes in light gray here. And I will use orange to draw these. Now, the points where x equals 0, that's the vertical axis. And the points where y equals 3 minus x, so y equals 3 minus x, that should be a line, and it goes through the point 0, 3, and the point 3, 0, and it has slope minus 1. So let me draw that in. Okay, so the thing that I've drawn in orange is this first nullcline. As a matter of fact, let me turn all of that orange. I'm going to sketch a little bit of the vector field. These are points where x dot equals 0. That means that the vector field points either straight up or straight down. And I don't really know for sure which yet, so I'm just going to draw little vertical hash marks. Now, at this point, there's really not an easy way to draw this on the vertical axis. What's kind of nice about that is that it means the vertical axis is something called an invariant manifold. Once you start on the vertical axis with y equal to 0, you stay there. That means that the vertical axis is actually a barrier, and no solutions will be able to cross it. Because again, if you start on the y-axis, if x is 0, I hope I said that right. If x is 0, then it stays 0 forever, and only y changes. So that means that the entire vertical axis is covered with solutions. And just to make this a little bit, what I want to do is erase that dot. Can I do this? Yes. There we go. Okay. So that's one nullcline. Now let me get a different color. How about this? I'm still not sure what color this is, but it's kind of pretty. Look at y times 2 minus x minus y equals 0. So now again, we've got a factor that tells us all points where y equals 0 and all points where y equals 2 minus x. Okay, well, the points where y equals 0, I bet I can draw better than that. That's the horizontal axis, and the points where y equals 2 minus x, that's going to be a line through there and through there. So let me draw that in. So the points that I've drawn in magenta there are solutions to g equals 0. That means y dot equals 0. So on these magenta lines, the vector field has to be entirely horizontal. Again, the horizontal axis lines up with the vector field. It is an invariant manifold. And what that means is that once y is 0, it stays 0. And again, that means that the horizontal axis serves as a barrier. It's completely covered by solutions to the differential equation. And since solutions cannot cross, it forms a barrier. Now we can look at this picture, and let me find another color here. How about I don't know, how about that one? The places where a orange line or curve crosses a magenta line or curve, those are the fixed points. So there's a fixed point there. Tell you what, let me draw it as a circle. And there's another fixed point over here, and there's a fixed point here. And our job will be to determine the stability and sketch the vector field somehow or another around those points. Now, it should be clear enough how to read these points out. That's 0, 0. That's the origin. This is x equals 0, y equals 2. And this is x equals 3, y equals 0. It should be clear from the equations that, first of all, 0, 0 will give 0 for x dot and y dot. And same thing for 0, 2. The x being 0 clears out the first equation, and then when you plug in y equals 2 and x equals 0, that zeroes out the second equation, and so on. So we found 3 fixed points. Now we need to use linear stability analysis to classify the 3 fixed points. And once we do that, we'll be able to come back to this picture and fill in some more details. So next thing we need is the Jacobian. Okay, so first, f of x and y is x times 3 minus x minus y. Okay, do you remember how to do partial derivatives? F sub x. Take a moment, work out the partial derivative, see what you get. Okay, 1 times 3 minus x minus y plus x times negative 1. There are other ways to do that, but there you go. So that gives us 3 minus x minus y minus x. So that's too close. 3 minus 2x minus y. G of x and y is y times 2 minus x. Oh, wait a minute. We haven't finished with f yet. Sorry. F sub y of x and y is, okay, now we need to do the derivative with respect to y. Take a moment, see if you can remember how to do that. Okay. This one has a particularly tricky bit because it's got stuff minus xy, and these cross terms are so easy to stumble over because when you do the derivative with respect to x, you get y, and when you do the derivative with respect to y, you get x. So watch out for those cross terms. We've done f sub x and f sub y. Now we need to do g sub x and g sub y. Okay, g of x and y is y times 2 minus x minus y. Partial derivative with respect to x. Okay, y times negative 1. And g sub y of x and y is zero 1 times 2 minus x minus y plus y times negative 1, which simplifies into 2 minus x minus 2y. Okay, so partial derivatives all over the place. Now let's write out the matrix. F sub x goes here, so f sub x, f sub y, g sub x goes underneath, and g sub y goes underneath on the right. Okay, f sub x is 3 minus 2x minus y. F sub y is minus x. G sub x is minus y, and g sub y, where did it go? 2 minus x minus 2y. So 2 minus x minus 2y. Did I do that right? 2 minus x minus 2y, yes. Okay, so that is the Jacobian matrix. Now, let's copy this. Come on, copy. No, copy. Copy. There we go. Copy this. I'm going to go on to the next page. Put that there. Now, our first fixed point was at 0, 0. Okay, so let's look at j of 0, 0. We'll fill in and get 3 here. We'll get 0 there. We'll get 0 here, and we'll get 2 here. This is a really nice situation because in a diagonal matrix, which this is a diagonal matrix, it's 0 everywhere except down the main diagonal. In a diagonal matrix, the eigenvalues are right there on the diagonal. The eigenvectors are easy to pick out, right? If A is equal to a diagonal matrix like this, then A times E1 right? This is E1, elementary basis vector number 1. When you work out that matrix product, what do you get? 3, 0, and that's 3 times E1. And I'll leave you to work this out for yourself. This is very easy to do. But there's E2. So the eigenvalues are right there on the diagonal, and the eigenvectors are just the elementary basis vectors. Now, since lambda 1 which is 3, is greater than 0, and lambda 2 equals 2 is also greater than 0. This fixed point is, well, what kind of fixed point happens when you have two positive real numbers for the eigenvalues? This is an unstable node. If you want to be a little more specific about it, you can imagine here's E1 and E2. Solutions are going to grow faster in the E1 direction than in the E2 direction. So that should give solutions that look something like this. Okay. So there we go. That's what we expect around 0, 0. Now our second fixed point, we come back over here. Well, we've got two more to choose from. Let's take a look at 3, 0 next. Okay, and let me do the same thing. I'm going to copy this, create a fresh page in my notebook, and paste. Okay, the fixed point at 3, 0. All right, well, j of 3, 0, that'll be a here, is, okay, 3 minus 6 minus 0, 0 minus 3 here, and what is this? 2 minus 3 here. So that gives us negative 3, 0, negative 3 here, and negative 1 there. Now, I mentioned on the previous example that when you do a when you're looking at a diagonal matrix, the eigenvalues are on the diagonal. It turns out that's actually also true for triangular matrix. So you can see here, this is a triangular matrix. So for a triangular matrix, the eigenvalues are on the diagonal. So that means our eigenvalues are negative 3 and negative 1. Okay, well, since lambda 1 equals negative 3, that is less than 0, and lambda 2 equals negative 1 is less than 0. This fixed point is, well, what do you think it is? This is a stable node. Now, to get the eigenvectors, that'll be a little bit trickier. So let me first do lambda 1. So what I've done there is form the matrix A minus lambda 1I. And you will see that it is indeed singular. What did I do here? That should be a negative 3. Let me get this right. Negative 3. and that'll be -1 minus -3, so that's 2. Okay, we need a vector, a non-zero vector, that's in the null space of this matrix. And there's always many to choose from, but this needs to be 0, right? Because we want this to be 0. And this one, we may as well just choose to be 1. Okay, so a times E1 is actually equal to -3 times E1, and you can check that out. So there's E1. There was the eigenvector that's easy to find. Okay. A minus lambda 2I. So this will be -3 minus -1. I want to be sure I'm doing this right. 0 here, -3 here, and then -1 minus -1. Okay, -3 minus -1, so this is -2. And then we have -3 here, and then -1 minus -1 is 0. Okay, this matrix has a row of zeros, so it's clearly singular. That's good, that's supposed to happen. Now all we need is a vector in its null space, and that will be the eigenvector for the second eigenvalue. Now if you'll notice, this row really doesn't help. Anything we put here and here, when we multiply it by this bottom row, we're going to get zeros. So that's really not a problem. But I need to be able to multiply something by -2. Oh, I don't know what to call this. So about, for right now, we'll just call it x and y. And just forgive me for using x and y again. -2x minus 3y has to equal 0. So y is -2/3 x. Okay, so any vector that satisfies that equation will work. Let's choose, I'll call it v2, and oh, if I make x be 3, then y can be -2. Have I done that right? If I make x be 3, then y is -2. And then, just to confirm, because it's been that kind of day, we're going to get -6 from there, and plus +6 from there. That's good. And then this row is no problem. And sure enough, yes, we get zeros. Okay, so what that means is that the fixed point at, what was this? This was at 3, 0, right? Yes. So the fixed point at 3, 0, 1, so 0, 1, 2, 3, 0. There's an eigenvector. Let's tell you what, let me turn this gray to make the rest of this easier to see. So there's an eigenvector in that direction, and then there's also an eigenvector where x is 3, minus 2. So there's an eigenvector kind of pointing off in that direction. The eigenvalue associated with the E1 direction is -3. So that will, the E3 component, sorry, the E1 component will, something's not right about this. Have I done this wrong? Yeah, I've drawn this upside down. I knew something was wrong. Because I need negative in the y direction. See, I know what picture I'm supposed to get at the end. Okay, that's what I wanted. Now, because the magnitude of this -3 is greater than the magnitude of the -1, the component of the solution in the E1 direction is going to decay exponentially much faster than the component in the other direction. So that's going to give solutions that look like this. So that's what things look like in the vicinity of, and I can go ahead and mark it green, of that fixed point. And this is just hard to read. Let me redraw that arrow. Yes, I'm a perfectionist. Okay, so there we go. There's the fixed point at 3, 0. We've got one fixed point left, which is at 0, 2. So let me copy this, go on to the next page, and paste. Oh, all right, here we go at 0, 2. Okay, we will let A be the Jacobian at 0, 2. So this is 3 minus 2, minus 2 here, 0 here, and 2 minus 4 here. And when the dust settles, you get minus 1 here, minus 2 here, 0 here, and minus 2 here. Except this can't be right. What have I done wrong? 3 minus 2 is 1, not negative 1. So again, I know what picture I'm supposed to get, and I'm able to look ahead a little bit. Again, we have a triangular matrix, so it's really easy to pick out the eigenvalues and the eigenvectors. It doesn't matter, upper triangular or lower triangular, same thing happens. But this time, one eigenvalue is 1, and that's positive. The second eigenvalue is negative 2, and that's negative. So since we have one positive and one negative, the fixed point is, well, what kind of fixed point is this? It is a saddle. Okay, now we need to figure out which direction is the attracting direction and which direction is the repelling direction. Okay, well, let's do a minus lambda 1 I. That will be 1 minus 1 minus 2, 0, minus 2, minus 1. So that is 0, 0 on top and negative 2, 3, negative 3 on the bottom. Okay. We need a vector in the null space of this matrix, a non-zero vector in the null space of this matrix. So this is another one where one row is not going to help at all, and the other row actually determines everything. So we need negative 2x minus 3y equal to 0. Let's solve this, and we get y equals negative 2/3 x. So we could let v1 be, well, I could let x equal 3 and y equal negative 2, which kind of looks familiar. And that will be the repelling direction because that's associated with lambda 1, which is positive. So this is the repelling direction. Then we need to do a minus lambda 2I. Lambda 2 is negative 2. Okay, so we need to do 1 minus 2, 0. Let's see what's the bottom left there, negative 2, and then negative 2 minus negative 2. Negative 1, negative 2 there, and 0 there, and 0 there. Okay, so again, we need a vector in the null space of this matrix, and this time I think it'll be pretty easy to just eyeball one. We have to put a 0 there because -1 times 0 has to give, we have to have the 0 here, which means that we can put anything, yeah, we can put anything there. Okay, so there's E2. So this is the attracting direction. Okay, so what does that mean? Let me draw some axes here. So there's the point. It's at 0, 2. The attracting direction is along the vertical axis. So the saddle looks like that right there. And the repelling direction is, well, it's kind of down like this again, and then the mirror image up there. So solutions look like this. And I'm going to draw, I usually draw saddles as a circle with a cross in it. It just looks like the right thing to do. Okay, so now we've got these three little fragments worked out. Now we can go back and add some detail to this picture. So I'm going to copy this picture and go here and paste it, and let's see, line it up, and actually I may as well make it bigger. Is that going to line up at all? Oops. Let's try this again. So what I really need to do, yeah, is, boy, and you can't really see it until you let go of it. Okay, that's probably about as good as it's going to get. Okay, now we can finish drawing all of this. So the fixed point at 0, 0 was unstable. It was a node. So we can draw vector field going like this. The one at 3, 0 was a stable node. And if you'll remember, we had something like this. And I can fill it in with green because it's a stable node. I'm going to tell you what, let me fill in, well, let me do like this. Let me make a red dot there for that. And finally, up here, this fixed point was a saddle. Looks something like this. I can add some arrows here like that. And if we go back to here, let's see, what did we figure out? That they should arc, that the E1 is growing faster than the E2 right here. So we have something like this. We have solutions doing something like this. So that tells us something now about these little arrow fragments that we drew along those null lines. And we can kind of fill in here. Well, actually, yeah, they're going to kind of hook around just a little bit there. And that is pretty much our face portrait. Now, there are a few things that we can fill in here. There's one last thing that we can fill in. This dynamical system has a very special property. This is kind of unusual. Let me show you what it is that I'm seeing. If you notice, it looks like there might be a solution that goes straight from here to here. Let me show you how to confirm that. It works out pretty nicely just because of some accidents with how this vector field is defined. So if you remember, we've got x dot equals x times 3 minus x minus y, and y dot equals y times 2 minus y minus x. I'm going to change variables and let w be 2x plus 3y. And then, just to be complete, I'm going to let z be equal to x plus y. Okay, w dot is 2x dot plus 3y dot. So that's 2 times x times 3 minus x minus y plus 3 times y times 2 minus y minus x. And when you go through all of this, you get 6x minus 2x squared minus 2xy plus 6y minus 3y squared minus 3xy. So you end up with 6x plus 6y minus 2x squared minus 5xy minus 3y squared. And by a sort of algebraic miracle, this factors like this. And there I've substituted for z and for w. The important thing about this is that if you'll notice, w equals 6 is fixed. Now, what that means is that if you choose an initial condition where w happens to be equal to 6, then w will be 6 forever. Because you can see that if w is equal to 6, then w dot is 0. What that means is that the line 2x plus 3y equals 6 is an invariant manifold. So again, once you start on that line, you stay on that line. Now, it's, like I said, an unusual feature. Sometimes vector fields do have these invariant manifolds. And in fact, you can look at this one. There has to be one, and I'll say more about that in a moment. But it's unusual to be able to pin down exactly what it has to be. So first, before we go any farther, I'm going to show you a numerical result. Well, switch. There it goes. Okay, so this is the result of stream plot. And right here is the fixed point at 0, 0. Right here is the fixed point at 0, 2. and over here somewhere is the fixed point at 3, 0. Let me see if I can zoom in a little bit and make these fixed points a little easier to see. Maybe. Okay, so there's an unstable node here, there's a saddle here, and then there's a stable node here, and right down here is that stable line, which was, what was it again? 2x plus 3y equals 6. Now, getting back to why there has to be why there has to be an invariant manifold like that. I'm going to sketch this again without quite so much detail, and just draw the 3 fixed points and draw in the barriers along the axis, the horizontal axis and the vertical axis. Okay, the saddle has a stable manifold, which is the line of points that comes in, but then it also has this unstable manifold. These are points that converge to the saddle if you reverse time. Now, why that's important is that if you reverse time, then points over here in the positive quadrant have to either come from the origin or they have to come from way out somewhere. So if you start at a point somewhere here, it either has to backtrack from somewhere far away up here, or it has to backtrack to 0, 0. Well, there has to be some kind of barrier, some kind of division between the points that came from here and will backtrack in reverse time out to infinity, and the ones that backtrack to the origin. Well, that's where this invariant manifold comes in. The unstable manifold of this saddle actually goes from the saddle and converges in forward time to the fixed point over here. This is a special kind of trajectory. This is called a heteroclinic trajectory because in forward time it converges to one fixed point, and in reverse time it goes back to a different fixed point. There's also such a thing as a homoclinic point, which is one that tends to the same fixed point in forward time and in reverse time, but from different directions. This barrier, so this trajectory that goes from the saddle to the stable fixed point is what forms the barrier between the trajectories that came from 0, 0 and the trajectories that came from way out here. So this is where geometry comes into play, and things like how these 3 lines form a trapping region. Trajectories cannot cross the axis because there's a trajectory here. Trajectories can't cross this axis because there's a trajectory here. And trajectories can't cross that line segment because, again, there's a trajectory there. So this is where, even though we can't easily get a algebraic closed form solution to this differential equation, we're still able to get a lot of information about what its solutions do. And we can confirm things that this is a population model. So x and y, if they start out positive, they should never be able to go negative because you can't have negative animals in a population count. And that is indeed upheld by the fact that there are trajectories up and down the horizontal and vertical axes. Also, it is typical in population models to be interested in the question of extinction. In this case, since the origin is unstable, that means extinction is unlikely, because if you were to set up this system somewhere close to 0, 0, so which would be the extinction of both species, it would run away. Having said that, the species represented by y is probably going to go extinct because all of the trajectories eventually converge. Well, all the trajectories in this positive quadrant eventually converge to this fixed point where y is 0. So the interpretation of this is that one species must go extinct and the other species will settle down to a stable equilibrium. Okay, so there you go. That is linear stability analysis and a little bit more for this dynamical system in the plane.